For a little more complicated example of area and polar, we're going to look at the area between two polar curves. Not going to make it super complicated, but we want to find the area inside r equals 2 sine 2 theta and outside r equals 1. Well, first of all, we have to remember what those look like. I'm not going to do the full process of sketching. R equals 1 is pretty easy. That's the unit circle. I'm going to put the 1 there. R equals 2 sine 2 theta. That's one of the so-called roses. They don't really look a lot like roses, but they look like sort of like flowers. When theta equals 0, r equals 0. So when I'm pointing the radar beam this way, it's actually at the origin. As sine 2 theta grows, it's going to go out away from the origin. That's going to max out when 2 theta is pi over 2, or in other words, when theta is pi over 4 and r is going to be 2. So it's going to go out to here. And then come back, and when theta is pi over 2, 2 theta is pi, sine of that is 0, and it's going to come back. And then it turns out to just repeat the pattern, but it's a little bit tricky, because then when theta is between pi over 2 and pi, 2 theta is between pi and 2 pi, and so the sign is negative. So, but remember what that does, our convention is that you face in a certain direction, like say 3 pi over 4. If r is negative, you actually plot something, you actually walk backwards and you plot something down here. What it turns out to do is it gives you a symmetric leaf down here. I'm pretty bad at symmetry right now. And then when theta gets to pi to 3 pi over 2, 2 pi is now between 2 pi and 3 pi. The sign is positive, so now I'm hitting the front side in the third quadrant. So I get another symmetric leaf down here. And then I get another backwards leaf when theta is between 3 pi over 2 and 2 pi. 2 theta is between 3 pi and 4 pi. And I would think I'd be plotting it over here as I finish up the loop around with the radar beam. But again, I plot a backwards copy. Not amazingly symmetrical, but it really is supposed to be. Okay. If you want a better picture, I had Desmos do it. And that's what it really looks like. So notice that you've got 4 equally shaped lobes fitting the description inside sine 2 theta and outside that unit circle. And so that's going to be very useful. This is a good place to use symmetry and just do part of an object and then multiply by whatever symmetry factor. Because remember, this stuff over here is really tricky. This is where r equals +1, and it's being plotted in the forward direction with theta actually between pi over 2 and pi. But this lobe of the 4-leaf rose is not coming from theta is pi over 2 to pi. It's actually coming from theta is 3 pi over 2 to 2 pi, but plotted backwards with a negative r. It can get very confusing. In fact, the further you go with polar, sometimes you just stop allowing the negative r, or being very, very skeptical of it. And so it's really nice to know that in the first quadrant here, r is going to be positive. Here's where theta was going between 0 and pi over 2. 2 theta was between 0 and pi. None of this tricks with like facing one way and walking backwards to graph the thing. You can get in real trouble and get some really wrong answers if you're not careful with areas and the negative r's. So we're going to take, let's see, let me take us back to this thing. So we're going to take just 1/4 of that. We're going to look at this, and we're going to multiply that by 4. So, but we still need to know what the limits are. Well, let's set it up. So we've got the area here. It's just like the area between two curves in Cartesian. We're going to look at, we have our little sliver, and it's really the area between, we're going to approximate it as the area between two circles, with like an R1 as the outer and an R2 as the inner. And so we're going to have 1/2 R1 squared. That would be if you went all the way out there, minus what's inside the 1/2 R2 squared, all times 2 theta, R2 squared. In this case, and I'm purposely not filling the A and B yet because I'm going to need to figure that out from some intersection information. We've got 1/2 of 2 sine 2 theta all squared. I need another parenthesis. Okay. And then I'm going to factor out the 1/2 and then just minus 1. Okay. So very similar to area between two curves with y equals f of x, but it's always the 1/2 r squared d theta that you're starting from. Okay, so now what about the A and B? That's going to be where these intersect. So as I'm sweeping the radar beam around, when it's really close to the x-axis, when theta equals 0, I'm not hitting this interesting region that I'm supposed to be doing. I start to hit it right here where they intersect. Then I'm going to be hitting stuff. All this stuff gets filled in by the radar beam. I'm going to erase this stuff because this stuff is not going to get filled in. And then it's going to be, it's going to stop hitting it right where that other intersection is. So very similar to area between two curves in Cartesian, you have to find the intersections by setting up an equation. Okay, so r equals 2 sine 2 theta, but also equals 1. So sine 2 theta is 1/2. And so we're going to get 2 theta is going to be pi over 6, or 5 pi over 6. And so theta is pi over 12 and 5 pi over 12. Let's go back to the pretty picture for just a sec. So again, we're looking at the radar beam sweeping out. It's not going to hit anything until here. Then it's going to sweep until it hits over here. And so it turns out that this is pi over 12, and that's 5 pi over 12. Hopefully that looks pretty plausible on the pretty picture. Okay, so now we know what our limits are. It means we're not going to get amazingly pretty numbers here, but you have to contrive the heck out of these guys to get super pretty numbers. Although we have a 2 theta, so it's not going to be too bad. Okay, well, I probably shouldn't have erased the picture, but oh well. Okay, I need the space for the algebra. Okay, so the 1/2 comes out. And then I'm going to go ahead and square that out. 4 sine squared 2 theta minus 1 d theta. And I'm going to need to do a power reduction again. Notice that even if you don't intend to square your trig functions, this is a great place where it's inevitable. You're going to square the trig functions. Really common place where you're going to do a power reduction formula. Okay, and so this is 4 sine squared is going to be 2 times 1 minus cosine. Now it's 2 times 2 theta, so it's 4 theta. And then still minus the 1. And now, let's see, I can, let's simplify that. Pi over 12 to 5 pi over 12. So 2 minus 1 is going to be a 1 minus 2 cosine 4 theta. Okay, we're getting close. And so we're getting 1/2. Okay, so now we can anti-differentiate. We got a theta minus 1/2 sine 4 theta, all from pi over 12 to 5 pi over 12. Okay, so up at the top, it's going to be 5 pi over 12 minus 1/2. So this is a nice thing. The 4 is actually going to make this into a fairly standard kind of value, so we don't have to go to a calculator or anything. So 5 pi over 3, and sine of 5 pi over 3 is a minus root 3 over 2. Oops. Okay. So that's part of it. And then minus pi over 12 minus 1/2. And then 4 pi over 12 is just pi over 3. And that's root 3 over 2 with a plus. And we just about got our number, and we'll make sure to check it to see if it's reasonable. I'll put it over here. 1/2 times, okay, 5 pi over 12 minus pi over 12, 4 pi over 12 or pi over 3. And then we've got a plus root 3 over 4 plus another root 3 over 4, so that's a plus root 3 over 2. Okay, very, very roughly, pi is about 3, so that's about 1. Root 3 over 2 is a little less than 1, but just call it 1. About 1 unit of area. And let's see if that makes some sense. Let's go back to our pretty picture. So we're looking at, remember this was just this part. And we haven't multiplied it by 4 yet. But these are unit squares right here. And it looks plausible that it's comparable to that. Maybe a little less, but then it's about what we're getting. Root 3 over 2 is not quite 1. So that's plausible. And so the total area is going to be 4 times that. And so it's going to be 2 times pi over 3 plus root 3 over 2. Okay.